This is a snapshot video on confidence intervals. Basically, one, you should be familiar with working with the Z table and the T table. I am not going to be showing you how I find those particular values. For one reason, you might be working with a table that looks slightly different than mine. Second, the values are going to be the same. It's just that the tables might look a little different. But anyway, the second thing, you should be familiar with this. You should have read over the material, looked at something in terms of what confidence intervals are. I kind of summarize it here on the first 2 pages. So if you haven't read through this, you should stop the video and work it out. All right, so again, we're going to be looking at 3 particular cases. I'm going to work examples for 3 particular cases here. All right, and those 3 particular cases are, let me get my table moving here, if I can do that. Okay, we got the table moving. All right, now we have 3 cases. We got 3 formulas. We know we're going to be working with confidence intervals, right? The question is, do we know the population standard deviation? If we do, here's our formula. Notice we're working with the Z table. If we're looking for a confidence interval and we do not know sigma, we can working with the sample standard deviation, and then we're going to be working with the T table. Okay? Again, you should be familiar with these. Third, we might be talking about a confidence interval associated with the proportion, percentage of a population, a ratio, etc. That is, if we're asking a question that says certain percentage like this, pass, fail, defective, percent that are good, we're working with the proportion. And if we're working with the proportion, our formula is given here. We notice we always work with the Z table because we can always calculate the standard deviation for our best point estimate p hat. Remember, p hat is associated with, forget that, let's get rid of that there, huh? Remember, this is unedited. If you are following this video, then you have to just kind of work with me here with any issues. I don't edit these things. All right, so anyway, p hat is the sample proportion, right? But again, we'll get into that. You should be somewhat familiar with all this, right? Okay, so I'm going to go right to my very first example here. Again, it is assumed that you have worked out the problems, or at least attempted to work them out, right? All right, our first problem. At the old light bulb factory, a sample of 30 light bulbs was taken, and it resulted in a sample mean of 869, and we want a 95% confidence interval. So right off, we know what we're looking for, a 95% confidence interval. Do we know for the mean, right? Confidence interval for the mean. So we know the population standard deviation, so we know the formula that we will be working with is X bar plus or minus Z times sigma of X bar. Okay, so in other words, we're looking for an interval that we have 95% confidence in, the true mean being located in that interval. We use the central limit theorem to find that interval that is going to be centered at the sample mean, X bar. Here's the formula that we'll be working with. So we need to know what X bar is. That comes from the problem, right? 869. We need to know what Z is. Z is the Z score associated with a 95% confidence interval. If you look that up, it turns out to be 1.69. We need to know what sigma of X bar is. Again, sigma of X bar from the central limit theorem is sigma over the square root of n. In our problem, that is 20 divided by the square root of 30. We have 30 light bulbs, right? If you do the math, that comes out to be 3.6515. If we multiply Z to sigma of X bar, meaning 1.69 to 3.6515, we get a product, and that product is 7.1569. Again, I'm not focused on the calculations here. That's your job. I'm focused on understanding the concept. All right, so I did my calculations here. I'm ready to work with the formula here. So I am going to be adding and subtracting this number from the sample mean. When I do that, when I add it to it, that's going to be the upper limit, right, on the interval, the upper bound on this interval. When we add those two numbers together, I'm going to round to two places, 876.16. So you should be very close to that number, within, the hundredths place, right? 0.17, 0.15, somewhere in that neighborhood. Okay? All right. When I subtract this number from 869, I get 861.84 interval that I am 95% confident the actual average lifetime of a light bulb, okay, that's what this problem really is about. I left that out actually, but there's my first typo. The average life of a light bulb is going to be somewhere between 861.84 and 876.16 with a 95% confidence. All right, so if you didn't get that, rewind the video, watch it over again. Otherwise, stop the video and work out this very next problem, which I'm about to do now. Questions are arising regarding the weight of beignets at the coffee stand in the park. All right, a sample of 11 beignets found that the sample mean was 3.5 ounces. Sample standard deviation was 0.2. I want a 98% confidence interval for the true population mean. So again, I'm looking for a confidence interval. I do not know the population standard deviation. So I am going to be working with the t-table. I will be working with the formula x bar plus or minus t times s of x bar, right? Because I have the sample standard deviation here. T is associated with the t-table. First, I need x bar. That comes from the problem. And that turns out to be 3.5, right? 3.5 ounces. I need t from the t-table. When I'm working with the t-table, I need the number of degrees of freedom. Since I have a sample size of 11, the degrees of freedom is going to be equal to 10. I'm looking for a 98% confidence interval. If you look this number up in the t-table, you should find 2.764. That's the t-table score, right? Now, I now need the sample standard deviation for the mean. Again, by the central limit theorem, this is going to be s over the square root of n. S in this particular problem is 0.2. The sample size is 11. Do your calculations, and your calculation of this should come out to be 0.1667. I'm sorry, I'm ahead of myself. Okay, not that. Okay, I'm looking at the wrong page. All right, 0.0603. I'm going good now, huh? T times s of x bar, that's what's equal to 0.1667, okay? So now I'm going to add and subtract this value, which again was the product of t and s. I'm going to add and subtract this from x bar. When I do that, I'm going to have an interval, and that interval is centered at x bar. And I'm going to have a 98% confidence that that true population mean, the true average weight of a beignet, is going to be between the two numbers I now calculate. When I subtract this number, 1.667 from 3.5, okay, I am going to get 3.33, rounded to 2 places. When I add it, I'm going to get 3.67. Okay, that's a 3. Okay, that's a 3 here. Let me erase that. Might as well. So 3.67. This is an interval that I'm 98% sure the average actual true mean beignet weight is between those two numbers. All right, move on to the next problem. Again, work it and then watch the video. All right, so moving on to the next problem. Next problem is a proportion problem. All right, so we might need to remember a couple of things about proportions because we don't normally work with them. But again, we're back at the old light bulb factory and we took a sample of 20 light bulbs and we found that 3 of them were defective. I want a confidence interval for the true proportion of bulbs that are defective. So again, I'm looking for a confidence interval, but this is a confidence interval associated with a percentage or, quote, a proportion. Now, the formula for this one is going to be p hat plus or minus z times sigma of p hat. P hat is associated with the sample proportion, right? So from our sample, P hat is equal to 3 defects divided by 20 light bulbs, right? In total. P hat, when we calculate it, comes out to be 0.15. 1 minus P hat, which I typically associate with Q hat, is then going to be equal to 1 minus this, which is 0.85. Right? Because remember, P hat's associated with the proportion that's defective, then the opposite of that is the proportion that are good. So 1 minus that, right? Okay. The next thing I need is Z, because again, with proportions, we always work with the Z table. I need the Z-score associated with a 90% confidence interval. Show yourself that this is 1.645. I need the standard deviation for the sample proportion. That's a formula. Sigma of P hat is the square root of P hat times 1 minus P hat over N. That is the square root of 0.15 times 0.85 divided by N, which is 20. That is the square root of that entire quotient there. So when you do your math, you should come out with 0.0798. So when I now multiply Z to this number, I get Z times sigma of P hat. That turns out to be 0.1313. So I have everything I need for my formula, but basically remember, we're looking for a confidence interval. That confidence interval is centered at the sample proportion, 0.15. We're going to add this number, and we're going to subtract that number. When you add it, you're going to come out with 0.0. I'm sorry, wait, hold on. I got to check this right quick here. Let me erase that. I might as well use my eraser, huh? All right, let me pause this for a second here. Okay, I did catch a calculation mistake. All right, anyway, when you add this, you're going to get 0.2813. When you subtract it, you're going to get 0.0187. That is my 90% confidence interval for the mean. I am 90% confident that it's going to be in that particular interval. Now, this is pretty extreme, and the reason why, really, I'll just point it out, is the sample size is rather low here. And for proportions, this sample size really needs to be high. Otherwise, you get really a very wide range of values here. Okay. Anyway, I think that was the last problem. I hope this helped a bit. Once again, you should watch the video only after you attempted the problem. So good luck with everything. And again, if for some reason you find a mistake, let me know. It might be a mistake in calculations, but it's not a mistake in terms of concept. Okay. Anyway, but I'm pretty sure because I worked them out ahead of time. I cheated. All right. So anyway, good luck.